Alright, so we just looked at all of the physical properties that we're going to use in lab to distinguish our minerals and the ones that we use as geologists whenever we're in the field and can distinguish them in such a manner. So now we move on to mineral groups. There are more than 4,000 minerals that have been named and several new ones that are identifiable every year, or identified every year. Fortunately for students who are just beginning to learn about mineralogy, only a couple of dozens are truly important, and even geologists like me, for the most part, don't know more than 1 or even 200 of them. So that's useful, I guess. The ones that we will learn here in the lab are the rock-forming minerals, the ones that make up most of the rocks on the Earth's crust. Some other minerals, which we will not look at necessarily, are called economic minerals, which are used extensively in the manufacturing of products. Sometimes these minerals are abundant in certain areas, but they tend to appear concentrated in certain rock types or near specific geologic features, these economic minerals. There are also accessory minerals, which typically make less than 2 or 3% of a rock. So sometimes economic minerals or even the rock-forming minerals can be accessory minerals in a specific rock sample. So if I have, say, a rock sample that has only 2% quartz, quartz in that case is an accessory mineral, even though quartz, as a bigger picture, is a rock-forming mineral. Alright, so next we will be looking at minerals and their subdivision into groups. Geologists split them up in a similar classification as to which biologists classify living organisms. So into, the taxonomy of living organisms goes domain, kingdom, phylum, class, order, family, genus, and species. A classification of minerals is also kind of done this way. So this classification of minerals is done by minerals' characteristics. So the internal structure and chemical composition tend to dictate to which group and subgroup of minerals each sample belongs to. And there are also subclassifications for these minerals within each of the groups, as I had said. But we will just go over the main groups into which they are subdivided. Important mineral groups are going to be the silicates, carbonates, halides, sulfates, sulfides, oxides, and native minerals. Before we jump into talking about the specific groups, it's worth mentioning the amount of the different elements that the crust has for mineral formation. So about 98% of the rock-forming minerals are composed of only 8 elements by weight. Okay? So those elements being oxygen with 46.6% in abundance, silicon with 27.7%, aluminum with 8%, iron, potassium, magnesium, and sodium, and calcium with some smaller amounts in this. So from these minerals, from these elements, oxygen and silicon are the two most abundant elements that we have for formation of minerals. And commonly, both oxygen and silicon bond together to form the most basic building block, if you would, of the most common mineral group, which is going to be the silicates. Okay, so silicates comes after silica, which is silicon and oxygen put together. The building block that they form is called the silicon-oxygen tetrahedron, and it is a pyramid-like structure with 1 silicon atom in the middle and 4 oxygen atoms making the corners of the pyramid, or the prism, if you would, which is right here on this image on the right. So far, about 800 minerals have been found to belong to the silicates group, which itself makes up 92% of the Earth's crust. Okay? So again, 8 most common elements are those outlined here on this image. The mineral group that has the greatest amount of rock, or forms the greatest amount of rocks in the crust, are the silicates, with 92% of them being silicates. Okay? All right, and the silicates themselves, which are the most abundant mineral group, are made up of these silicon-oxygen tetrahedra, which is the basic building block of them. This is very important, and you'll definitely be tested on it. Okay, the remaining mineral groups, so again, those are the carbonates, halides, and whatnot, are just paired usually into the non-silicate classification because they're not nearly as abundant as the silicate. All right, so the silicon-oxygen tetrahedron, or SiO4, is a complex ion. So it forms from a covalent bond of the silicon atom and 4 different oxygen atoms. And by their bonding, it basically has a charge for this complex ion of -4. So to become balanced, this complex ion needs to bond to other positively charged ions. Okay, so it needs to have some sort of extra ionic bonding to its structure, typically. The simplest silicate structures are those of independent tetrahedrons that have their oxygen atoms bond with positively charged ions such as magnesium or iron. These are typically called single tetrahedron structures. So those are going to be this structure where you just have the silicon oxygen tetrahedron bond with an element that has a +4 as the ionic charge. So based that silicate structure of single tetrahedrons, a good example of those or of that structure is going to be olivine, which is this mineral that you're seeing right here. But just like olivine, we have, for example, garnet, which is another good example of this single tetrahedron structure. Both of those lack cleavage due to their chemical structure being the way it is. So every bond within the structure is very strong, and so there's not going to be any planes of weakness per se. However, for example, they do have crystal habits. So for example, garnet forms in dodecahedral forms upon growth, which is pretty cool. All right, so silicon oxygen tetrahedrons can link to each other in a variety of configurations as well. This process is called polymerization, and it happens by sharing 1, 2, 3, or all 4 of the oxygen atoms with adjacent tetrahedrons. Many of these tetrahedrons then join to form single chains, double chains, sheet structures, or 3-dimensional frameworks. So you're seeing single chains right here. So in this case, only one of the oxygen atoms is bonding with another silicon oxygen tetrahedron. Double chains, so you have 2 or 3 of them. You have sheets, which is for the most part 3 of them. And then you have the 3-dimensional networks that occur as well. So figures 3.24 and 3.25 of your book are great for understanding how the silicon oxygen tetrahedron bonds with other silicon oxygen tetrahedrons out there to create the different silicate structures that we have right here. Okay, so the most common silicate structure is that of 3-dimensional frameworks, which is right here. So quartz and feldspars, which are the most common minerals subgroups, have this specific 3-dimensional network structure. It is then fairly clear that the more complex the structure is, the greater the silicon to oxygen ratio is. So many times silicate minerals are described as having a low or high silicon content based on the ratio, and this will become important to remember for understanding some of the concepts in chapter 4 better. So again, the more complex the structure, the greater the amount of silicon there is per amount of oxygen. So both quartz and feldspars tend to be more silica rich, which again will make sense on chapter 4. It's a super key concept to understand right now. Okay, so to try to bring it all together, the silicon tetrahedron having a -4 charge as a complex ion needs to bond to positively charged ions in almost all of the cases. And these ions are usually iron, magnesium, calcium, sodium, aluminum, and potassium. So the other main 6 elements out there, or the most abundant 6 elements out there. As a general rule, the covalent bonds between silicon and oxygen are stronger than the ionic bonds that hold one silicate structure to the next. Consequently, properties such as cleavage and to some extent hardness is also another one, are controlled by the nature of the silicate framework, or that silicate structure. Quartz, for example, only has silicon-oxygen bonds, which makes it equally strong in all of the directions. So it is hard and does not have cleavage. Okay? So those are both measures of strength, if you guys remember the physical properties. As a contrast, talc, which is a clay mineral, has a sheet structure with magnesium atoms in between each of the tetrahedron sheets. So if you can imagine this sheet, imagine the one magnesium atom is being, I guess, bonded here with this top of the oxygen, all on top of all of the oxygens that are up here, right? So that magnesium atom bonding each of the different tetrahedron sheets makes it very easy for each of these sheets to slide past one another and be so soft. So that's why talc, the mineral, is itself so soft. Very easy for those sheets to slide past one another. So another thing to keep in mind is that atoms of similar size can substitute freely for one another without necessarily altering the mineral structure. For example, in olivine, iron and magnesium substitute for each other all of the time. So they make 2 different end members of olivine, one being grossular, the other being almandine, but they're still within the same mineral name, which is olivine. The same thing happens, for example, in plagioclase feldspars and even potassium feldspars. Potassium, calcium, and sodium kind of interchange, and one of them is going to be the one occupying that space. So these substitutions allow for certain mineral subgroups, as I said, to have certain end members, as is the case for olivines, pyroxenes, amphiboles, micas, and feldspars, as I said. So we'll go through a few examples later in the lecture, as well as the lab.